Today, our speaker is Andrii Ilienko from Polytechnic University of Kyiv, and the talk will be about strong limit theorems for Tukey depth regions. Please.
Okay, thank you. Presentation. Yeah. Is everything good? Can you see my presentation?
Yes.
Yeah, okay, thank you. First of all, I am grateful to the organizers for the kind invitation to this seminar. And unfortunately, my topic is not related to Malliavin will still be interesting for you because it covers statistics and theory of probability in Banach spaces in the spirit of Ledoux and Telegram and so on. This is talk based on our recent paper with Ilya Molchanov. And maybe I will start. So first of all, I will give a so extended introduction because in some sense there were two approaches to my topic. Geometrical approach and statistical approach, and they are related. And first of all, I will start with geometric setting. So let we have some compact convex sets with a convex set with non-empty interior, and let us consider actually a standard setting in stochastic geometry. So we take a sample of independent points, uniformly distributed points in this body, and let us consider their convex hull as depicted in this picture. And it is clear that if M is quite large, if N tends to infinity, convex hull tends in some sense, in many different senses, for example, in Hausdorff sense, to convex body K itself. And a natural question is, how good is this approximation? Actually, there are several different approaches to answer this question, because there are different measures. How can we measure the quality of this approximation? Maybe from the point of view of stochastic geometry, the most maybe not natural, but the most classical way is to bound these missed volumes of this the body K itself and this convex hull. But there are many different papers on this topic, and actually this is absolutely classical object of study, because even if in classical papers by Renier and Zlonke this question was posed, and there are many interesting results about these missing volumes. Maybe the most interesting from my point of view is so-called Efron identities, which call that if we consider this missed volume of K minus convex hull, maybe I will take convex hull number n plus 1 and multiply this by, but take expectation. This is, if I'm not wrong, now vertices in this convex hull. So how many points do we have here? How many exterior points do we have here? And what is interesting, this equality is not asymptotic. It holds for each fixed n. But from purely geometric point of view, maybe this is characteristic because it is not quite geometric. From the point of view of pure geometry, it is more natural to use the Hausdorff distance, because Hausdorff distance takes into account not only volume, but also a shape of our sets. Maybe I will recall what is Hausdorff distance. Maybe it is well known, but for the case. So actually, Hausdorff distance, let us take two closed sets and maybe even closed convex sets and bounded, so compact. And how we can inflate our set A in such a way that this inflated set covers B and vice versa. And this minimum inflation epsilon is called Hausdorff distance between these sets A and B. The set of compact convex sets equipped with Hausdorff distance is very good, is a separable, complete, and even locally compact by Blaschke selection theorem. And in terms of this Hausdorff distance, our question is, from my point of view, the most natural. So what is known about distance of Kn hat and K in terms of Hausdorff distance? Actually, not very much. There are only two known results. The first one by Imre Baranyi, that if our original convex body is sufficiently smooth and actually strictly convex, or more precisely is of positive Gaussian curvature, that there is a good estimate for expectation of Hausdorff distance between K and hat, only in terms of order, because there is some constant here, and this constant is not known, and moreover, this constant depends on our set, but there is some result, such a result. And the second result is by Lutz Jumken and Günther Walter, not about expectation, but about rate of convergence, that in any case, this rate is O small of logarithm n divided by n to the power 1 over d, and under some mild smoothness assumption, we can make this order even better. But actually, these are only two results which are known about Hausdorff distance. And our aim now is to a bit shift the perspective. And actually, our question is what happens in the interior of our set, because all these results are in some sense boundary results. They bound.
Excuse me, I have a question.
Yeah.
Is this topic related to the such well-known questions as convergence of empirical measures?
Exactly.
Yes, so it reminds me Vapnik-Chervenenkis classes and so on. Yeah,
it is very related with this topic.
Okay.
But even more related is what follows our results, because these are boundary results. But to embed this in the topic of empirical measures, we should shift the perspective and consider what happens in the interior of our set. And the most natural object for this study is so-called convex floating body, which is a standard object in modern stochastic geometry. What is convex floating body? Actually, this is the definition. So we intersect all half spaces, all closed half spaces, which are in some sense quite rich. So volume of intersection of H and our body K is greater than some 1 minus alpha multiplied by this volume. And maybe it is more clear on the following figure or on the following picture. So we cut off from our set K all caps of volume, some fixed alpha multiplied by this volume of K. Maybe it is something strange that here we have strict inequality greater, because it would be more natural to have strict equality. But for uniform distribution on convex body, it is absolutely the same. We can write equality, we can write strict or non-strict inequality. All this is same. But when I will consider not necessarily uniform distribution, but general probability measures, because of some possible degeneracies, it is more convenient to use strict inequality. So the sense of floating body is as here. So we cut off all small half spaces. And this floating body is, as I have said, a standard object now in geometry, even not stochastic, but usual geometry. And now some examples. Now we can see floating convex floating bodies for square and for triangle, for different alpha. If we increase alpha, if we take alpha tends to 0. In this case, floating body is just K. If alpha takes maximum possible volume, maximum possible value, then K of alpha is some center of our body, if such center does exist. Yeah. And now we can introduce an empirical counterpart of this convex floating body. So actually the same approach, but now we use only some sample of random uniformly distributed points in our K. And actually we are doing the same. So we intersect all closed half spaces which are sufficiently large, so which contain most points of this sample. And if alpha tends to 0, in this case, K hat empirical convex floating body tends to convex hull of our sample points. And now I can formulate my aim, but only in limited case of uniform distribution on convex bodies. So in this special case, our aim is to estimate the accuracy of this approximation in terms of, first of all, Marcinkiewicz-Zygmunt strong law of large numbers, and what is much more interesting in terms of law of iterated logarithm, and in two senses, in sense of set inclusions and also in sense of the Hausdorff distance. But now let us go in the direction of empirical measures. So we extend our scope now, and let now mu be an arbitrary probability measure, not necessarily uniform measure on some convex body, maybe not absolutely arbitrary, because there will be some assumptions, but quite wide class of probability distributions. And let us introduce empirical measure. And moreover, we can get our results also in extended setting when these empirical measures are even weighted. So we allow for such weights. These are independent, identically distributed random variables, independent also of sample points XA. And actually, the only condition now that expectation is equal to 1. This is absolutely clear, because only under this condition we have unbiasedness of this estimator. And And now we can, in this extended setting, also define what does it mean. What does it mean? Theoretical and empirical convex bodies. So we use absolutely the same approach as before, but now we consider general measure mu and weighted empirical measure mu n. Okay, but what can be said in this case? Maybe it is also interesting that we allow for these weights, and we don't require that these weights are only positive, because it does not affect our proofs if psi can be negative with some positive probability. But if psi in some cases may be negative, geometrically it leads to some very interesting consequences. What I mean, as we know, k of plus 0 is just, it is quite clear that this is just convex hull of support of our measure. But what concerns k hat, these sets converge to convex hull only in case of positive weights. For example, if one of psi's is equal to 0, then actually our k hat does not see this point, so not all points take part in formation of this k hat. If we have negative weights, then also quite interesting geometrical effects can appear. So as before, k of alpha theoretical tends to convex hull of support, but k hat might not converge to convex hull. Okay, and now I would like to turn from geometrical setting to statistical setting, because it occurs that even before convex floating body became popular in geometry, a very related notion was popular in multivariate statistics. This is so-called Tukey depth, which was introduced in multivariate statistics in 1975 by Tukey. And what is Tukey depth? Let we have some probability, measure some probability distribution on multi-dimensional space Rd, and actually for each fixed point x, we define such a function, such a value d of x, which is infimum of all measures, infimum of measures of all half spaces which contain this set, this point x. So let we have some point x, and we consider different half spaces is here, and let us find half space of minimum possible content, and this minimum half space and its mu measure is actually Tukey depth. And it is quite clear that actually we can assume we can require here that x belongs only to the boundary of our half space, because only such a half space can be minimal. And why is it so important in multivariate statistics? Because actually this value d mu represents the centrality of this point with respect to distribution. So if we have a very small depth in some statistical realization, that maybe this point can be called outlier. So the higher d of x is, the more typical this point is for this distribution. And if our distribution is, for example, spherically symmetric, then maximum depth is attained just at the center, and this depth is equal in absolutely continuous case is equal to 1/2.
Excuse me, I have a question related to this definition. I am not very familiar with this topic of multivariated data, but it seems that half spaces can be replaced by some other regions, or maybe even we can introduce some kernels and so on.
Exactly.
So, yeah.
Yeah, it is possible. And moreover, I am almost sure that all our results can be transferred to the case when half space are replaced by some other objects, because actually from the point of view of the theory of empirical process, it doesn't matter. But I am not sure that all technicalities will hold, because many parts of our proofs are based on half spaces. But theoretically, it can be done.
Okay, thank you.
Yeah, and so maybe I will demonstrate now some known properties of this object of Tukey depth, which are quite interesting. So first of all, affine invariance. So if we replace our point x by affine transform of x, and at the same time replace mu but by image measure of mu under affine transform t, then nothing changes. It is absolutely clear, because affine transform map half space into half spaces. Okay, and the second property is, let us introduce such a condition, a very popular condition, that mu vanishes on each hyperplane. Then in this case, it can be proved that first of all, this infimum is attained, so actually this is just minimum, but not necessarily only at one half space. Maybe there are many minimal half spaces. And the second, in this case, this function Tukey depth in continuous in X. Next property. Vanishing at infinity. It is also clear just by intuition that if x tends to infinity, then depth tends to 0. What about maximum value of depth? First of all, this maximum value is always attained. So there is a Tukey median, or at least Tukey median set, when there are when there are several maximizers. And there are quite interesting inequalities for this maximum value. First of all, it can be easily checked that if mu vanishes on each hyperplane, then maximum value of Tukey depth is less or equal than 1/2. But there is also a lower bound, which is related to the dimension of our set. Actually, this is not very simple theorem, which was proven first of all in two-dimensional space, then three-dimensional, then also a general proof appeared. And this concerns any probability measures, and as for uniform distribution on a convex body, there is also such a bound that actually this is minimum possible value of maximum depth. For example, if d is equal to 2, this is 2 over 3 to the power of 2, so 4 over 9. And if we take any triangle, then Tukey median is just usual median, is center point of this triangle, and it can be checked that depth value at this central point is just 4 over 9. The next important property is Tukey depth regions. So maybe the main topic of my talk today. Let us consider such upper level sets, so where Tukey depth is greater or equal than some fixed level alpha between 0 and maximum possible value. And these Tukey depth regions are first of all compact and convex and nested. So actually, as we could see here on this picture, here alpha is, I don't know, let us write 0, 1, here maybe 0, 0, 2, 0, 3, and here 0, 5. So these sets are compact, convex, and nested. Okay, and now the most important of all these, the most important of all these properties is the property number 7, that introduced above generalized theoretical or empirical convex floating bodies constructed by a theoretical measure or by its empirical counterpart are precisely the same as these Tukey depth regions. So actually this set is just K of alpha, and this set for mu hat is K hat n of alpha empirical generalized convex floating convex body. And so now we can formulate the complete problem we address in this talk. So let us fix some fixed alpha between 0 and alpha max, and our main question is the rate of convergence of random sets K and alpha, which are the same as upper level Tukey depth sets, to deterministic limit K of alpha, and just again in terms of Marcinkiewicz-Zygmunt strong law of large numbers, and in terms of law of iterated logarithm, and also in two settings, in the setting of set inclusions and in the setting of Hausdorff convergence. Okay, and maybe it is reasonable now to mention one-dimensional case. In one-dimensional case, everything is much simpler. Because let us take any random variable, and just for simplicity, assume that cumulative distribution function is continuous and strictly increasing on the support. So in this case, we can uniquely define what are quantiles, left quantile and right quantile. And in this case, first of all, these quantiles are well defined, and the second, this Tukey depth region is just the segment between these two quantiles. In one-dimensional case, all limit theorems are known. Even law of iterated logarithm, and this law of iterated logarithm was proved by Helen Finkelstein in '71, and even in functional form. So without some fixed alpha, but some function of alpha. But in one dimension, everything is much simpler. First of all, because in one dimension it is quite usual that everything is much simpler, and also in one dimension we can use quantile transform. So actually we can from the very beginning assume that our random variable is uniform on the segment 0, 1, and it simplifies everything. But in multidimensional setting, we have no quantile transform, so we cannot limit ourselves just to the case of uniform distribution. So now I would like to turn to our main results in multidimensional setting. So first of all, assumptions on the measure mu. There will be several different assumptions, and I will not use all the assumptions in each theorem. Some assumptions will be needed in some theorems, some other assumptions in other theorems. But first of all, a very natural condition that our measure mu vanishes on each hyperplane, so it is not degenerate, and it of course holds for absolutely continuous measures. And why is it so important? Because under these conditions, first of all, Tukey depth is continuous function, and also that, as I have said, infimum in its definition is attained, but attained maybe not uniquely. So for each point, there might be several minimal half spaces. The second assumption is also very popular in all the theory. It is called contiguity of support, and actually it means that such a situation is not possible when we have some strip, and to the left of this strip we have positive measure, to the right of the strip we also have positive measure, but we have zero measure in this strip. Such case is not possible. Actually, this is the sense of this contiguity condition. And why is it so useful for us? Because by result by Massey Teodorescu, under these two conditions, this map, set-valued map, is continuous in the Hausdorff metric for all central values of alpha between extreme values. Okay, and now I will turn to the most maybe dangerous condition, a condition of continuous differentiability of depth function in X, in a neighborhood of fixed boundary of Tukey region. What does it mean? Let we have, for example, square, and we have some Tukey region is here. This is just boundary of this Tukey region. So I would like to have this function d mu to be continuously differentiable in some neighborhood of this boundary, and moreover that this derivative should be non-zero. Why this condition is so important? First of all, under this condition, we are sure that this infimum, which is attained by condition A1, is attained uniquely. So there is only unique minimum half space. And moreover, this map, this set-valued map under this condition, and also under condition A4, which follows, is not only continuous but also differentiable in the Hausdorff metric. But the problem is that this condition is, unfortunately, not as harmless as it may appear. In what follows, we will see that this condition is actually not needed for set inclusion theory, but this condition is needed for law of iterated logarithm in Hausdorff sets. But this condition is not harmless. For example, let us take
Andrei, I'm sorry. And what does it mean that the mapping alpha to k of alpha is differentiable? K of alpha, is it a set?
K of alpha is set. So this means that d Hausdorff between k alpha and k alpha plus epsilon divided by epsilon has some limit as epsilon tends to 0.
Thanks.
Yeah. So let us consider just smooth distribution. Usual Cauchy distribution, by the way, so two independent Cauchy random variables. And how can we find this Tukey depth? So actually, let us consider some point here, and let us draw some half space through this point. This point, let it be x1 and x2. So what is mu? What is measure of this half space? This is actually probability that, what does it mean that point x1, x2 is above hyperplane? This means that cosine theta multiplied by x1 plus sine theta multiplied by x2, theta is just this angle, is greater or equal than cosine theta multiplied by fixed point x1 plus sine theta multiplied by fixed point x2. But Cauchy distribution is alpha stable distribution, actually one stable distribution. So this linear combination is also scaled Cauchy distribution. So using this approach, it should be quite easily be found. This depth can be found quite easily, and so what this is Tukey depth. This is depth regions. So depth regions are squares in this case. And what is not quite good for us, then that this function is of course not differentiable. So it is quite a strange situation because distribution is quite smooth. What is non-smooth in Cauchy case? Maybe characteristic function, but characteristic function has nothing in common with Tukey depth. But for this smooth distribution, we have absolutely non-smooth Tukey depth. So actually this condition is not harmless, and it should be checked. And in most cases, there is only one way to check this condition, actually to find this Tukey depth explicitly. But it is also a hard problem because now, for example, I have a master student in KPI, and I have asked the student to find explicitly Tukey depth for a couple of independent exponential random variables, and it cannot be found explicitly. So to check this condition A3, we should have some result, and there is such a result. It is not the main result, so such a strange number -1, that if we deal only with uniform distribution, and moreover, if our convex body is centrally symmetric, not spherically symmetric, but centrally symmetric and also strictly convex, then it can be proved that this condition does hold. Centrally symmetric, yeah.
Can I ask you the question? It looks like this condition, especially the condition of differentiability, is related to some inequalities for this measure, like Ehrhart inequalities for Gaussian measure, and maybe Gaussian measure is such that everything is okay.
Yeah, for Gaussian measure, because Gaussian measure is central symmetric measure, spherical symmetric measure, it's everything okay. But I am not sure that this is related to such inequalities, because actually this is a local condition. It is very local, so we was not able to find general condition, and moreover, I spoke. I didn't speak. I have written a paper by Stanislav Naty, which is expert in this field, and he also writes that this is a very complicated question to understand in what cases this function is differentiable. Moreover, he has very interesting examples. For example, a mixture of two bivariate Gaussian distributions, a uniform mixture. So first Gaussian with probability 1/2, and second Gaussian also with probability 1/2. And if we take two different couples of non-degenerated Gaussian components of this mixture, in some cases we can get differentiability, in some other cases we can get non-differentiability. So it is very fragile, maybe it is called so condition.
I see. Interesting. Thank you.
Yeah, okay. And what is smooth if each point lies on a unique supporting hyperplane, and what is strictly convex, it is quite clear, boundary doesn't contain any symmetry. Okay, what about the proof? Proof is very technical, very geometric, but the main idea is not so difficult to prove such an inequality. Excuse me. Yeah, to prove such an inequality, that if we take some point x and two half spaces, and one of these half spaces should necessarily be minimal, so hx is minimal half space, and other half space is some arbitrary space, then we have such an inequality for difference of measures on these half spaces. And what is important for us, that the power is true. This power true ensures differentiability. Okay. Now, condition A4, last condition, looks not quite convenient, but this condition is quite innocent. It can be easily checked in any case, and in most cases, this condition does hold. So let us introduce a Radon transform of our density. First of all, we assume that our distribution is absolutely continuous with density F, and let us introduce such a Radon transform, which depends on point where we are calculating this transform and direction u. And this Radon transform should be continuous jointly in both arguments, and also it should not vanish for each x from some neighborhood of our boundary. I have said that actually this condition is easily checked, and in most cases it holds. Okay, and now what about why do we need these conditions A3 and A4? Actually, this is answer to the question by Andrii Ilienko. So we have such a differentiability, and moreover, we know what is the derivative. Derivative is 1 divided by minimum value of this Radon transform over all points of the boundary of the set K of alpha. I recall that alpha is always fixed. Okay, and now I can turn to main results. First of all, Marcinkiewicz-Zygmunt strong law of large numbers in terms of set inclusions. So let us introduce these weights and a moment condition on these weights. And in this case, we know that for all sufficiently large n, we have such a chain of set inclusions. What is interesting here? First of all, let us take p is equal to 1. In this case, we have just k of alpha is in k. Excuse me, p is equal to 1, here epsilon. Alpha plus epsilon is contained in Kn hat alpha, and also is contained in K alpha minus epsilon. This is usually a strong law of large numbers in terms of set inclusions. It is known in this theory, for example, from a paper by Dieterhoff about 10 years ago, but in non-weighted case. In our case, we have weighted empirical measures. But what is much more important, that actually we can use other moment conditions, any values of p between 1 and 2. For p is equal to 2, it doesn't hold because it is already the topic of central limit theorem, not of strong law of large numbers. But what is also interesting here, we have no moment conditions on the measure mu itself, only on weights. And this is also quite clear because we are now inside inside support. So what happens with our measure mu on infinity? It is not so interesting for us. So moment conditions on mu does not affect anything, and everything depends only on moment conditions on psi. And what about the proof? Maybe the K lemma in the proof of the theorem is such a lemma from the theory of empirical processes. So if n tends to infinity, here are empirical measures, here are theoretical measure, and usual statement with some flavor of the theory of empirical processes. And what about the proof of this lemma? Maybe I have not so much time now. The first idea is to embed all the setting into the classical setting of the theory of empirical processes. So we have actually two random objects: weight xi, let's say xi1, and sample point x. And if we introduce such an empirical measure of simultaneously xi and x, and introduce such a function fh, the function depends on half space h is from some countable family of half spaces. In this case, actually, our supremum, which we concern with, is just something like very standard objects, standard differences from the theory of empirical measures. And so at this time, the theory of empirical processes comes into play, and there are many results. And the theory, for example, result by Massart and Rio, actually Marcinkiewicz-Zygmunt law for empirical measures. And we can check this entropy condition, and it can be checked in our case. So actually our lemma is satisfied. And what is also quite good for us, we can, from the theorem and previous theorem about differentiability of Tukey depth regions, we can just get a corollary about Hausdorff distance. So in case P is equal to 1, we need the first two conditions. In the general case, we need second two conditions. And in this case, actually, we have also Marcinkiewicz-Zygmunt's law of large numbers in terms of Hausdorff distance. Okay, but what about Marcinkiewicz-Zygmunt setting? It is maybe not so technically complicated, because the most interesting part of my talk is the law of iterated logarithm. And so let us turn to this law. First of all, standard notation and assumptions. So usual normalization lambda n, and standard condition that the second moment of our weights is finite, and we fix some alpha between 0 and maximum possible value of alpha. And we have such an inclusion set since law of iterated logarithm. What does it mean? Now we take here lambda n here. Lambda n is just this iterated logarithm. And the question is, what about this number gamma? How large can this gamma be in order to get inclusions in such a form for the law of iterated logarithm? And it occurs that there is some natural boundary, this number square root of m alpha minus alpha square. And if gamma is quite large, in this case, we have set inclusions. If gamma is less than this critical threshold, then this set inclusions fail, because there are two sequences, nk prime and nk2 prime, that each of these inclusions can fail along corresponding subsequence. But what is interesting, for each positive gamma, our inclusions hold if we choose some corresponding subsequences. So for all subsequences, this holds only for large lambda. For small lambda, there are bad subsequences, but there are also good subsequences. What about the proof? The proof is very involved conceptually and technically. Maybe some outline of this proof. First of all, let us introduce this measure, product measure, law of weight times law of x, and let us consider some countable family of closed half spaces, and let us consider such a space of all bounded functions, but these bounded functions map half spaces into real numbers and equip this space by supremum law. The first lemma is empirical counterpart of law of iterated logarithm. Actually, this lemma is, in some sense, some remote consequence of the general compact law of iterated logarithm in Banach spaces, as in Ledoux and Talagram. Maybe it is more convenient to rely on some specific versions of this theorem, as in paper by Alexander and Talagram, but the sense of this result is actually as follows. We can introduce such a set K. This is actually a counterpart of Strassen ball in functional law of iterated logarithm. So this ball in the set L infinity contains some functions which map half spaces into real numbers, and ball of such a form, and it could be proved that this ball is compact set in this space L infinity, and actually it follows from Ledoux-Talagram law of large numbers in Banach spaces that we have such a convergence. So the set of limit points of these measures, by the way, these can be regarded not just as measures, but also as functions on half spaces, because each measure can be considered as a function of half spaces. So here we have
Excuse me, can I ask about the reason why it is compact? Because this W is in L2, or what? What is the reason why this set is compact in this L infinity? Because in L infinity it is sometimes quite hard, but sometimes it is not. So why it is compact?
I cannot say now why it is compact, because actually it is very complicated lemma. If I am not wrong, now, by Coelbs. It was proved by Coelbs maybe in 79. Then in all this compact law of large numbers in Banach spaces.
Yes, I remember work of Coelbs, but as far as I remember, the statement is that if we have the probability distribution for which the law we have a finite more second plus something, and we have separable Banach space, and I think we have some geometric condition on the norm.
Yeah, it may be entropic condition, but in this case, because actually we are considering now just specific case, in general case, if we take law of iterated logarithm by Ledoux and Talagram, and also by Alexander and Talagram, there are some entropic conditions here, but in our case, these entropic conditions are satisfied.
I see. Oh, entropic conditions is there is such book of Lipschitz and Werner. I think that they exploit this entropy
Maybe,
numbers, entropy conditions. Yeah.
yeah, maybe in such a sense.
It is related to small deviations because the next step is to check how this limiting compact set attracts the point of the sequence.
Exactly, yeah. This is one step away for small deviations. I absolutely agree. Yeah.
Okay.
So actually, why do we need this empirical compact law of iterated logarithm? Because actually, we are interested now in the boundary of this set K, and these boundary points of this Strassenball, these points actually matter because let us fix any half space, and the maximal deviation of empirical measure on this fixed half space from theoretical counterpart is controlled by only some, not all, but some boundary points. So the next step is to study these boundary points, and critical for us is the next lemma that actually, if we fix any fixed half space, and what is maximum and minimum values of function h, which are maybe here. No, actually, it is interesting for us to study H is from boundary K, from boundary of K, but actually this holds also for the whole. And so these two inequalities are instrumental for us because they allow us to control this maximum deviation, and actually these maximum values show why do we have such a constant here as square root of m alpha minus alpha square. And even we can exhibit explicit functions in which this supremum and infimum are attained. It can be found. These are such a function. And actually, at this point, the proof of inclusion law of iterated logarithm only begins, because the subsequent steps is very delicate and technically demanding derivation. So we can get all our 3 points studying some boundary points of the boundary of the Strassenball. I will not go in detail. It is not possible because the proof of the theorem is about 5 or 6 pages. But the main idea is study of the boundary points of Strassenball. Okay, and what about law of iterated logarithm in terms of Hausdorff distance? It can be also done. Actually, the theorem is as follows. What about lim inf? Why it is 0? Because the point 3 in our previous theorem is that for any positive gamma there is a good subsequence along which we have a good rate of convergence. So it is not, there are no particular problems with 0, but there are many problems with this limit superior, but it can be done by some technical machinery. And what is now interesting in comparing these results with results on the boundary of our set K? Let us return to our original settings. So just again, we study uniform distribution on some convex body, and in the smooth case, I cited a result by Jumkin and Walter that actually Hausdorff distance between a boundary of our set and convex hull of sample points behaves like here. But it occurs that in the interior, so if alpha is strictly between 0 and maximum value of alpha, we have absolutely another rate of convergence. And moreover, this rate of convergence does not depend on dimension, because here we have dimension 2 divided by d plus 1. Here there is no traces of dimension, maybe just only in the coefficient, because coefficient depends on Radon transform, and this Radon transform of density has implicitly some dependence of dimension of our space, but actually the order doesn't depend. And actually this is quite not surprising, because in one-dimensional case the situation is very similar, because for quantiles we have usual law of iterated logarithm, but for extreme values we have some convergence, like here. For if we take d is equal to 1, this is just 2 divided by 2, so something like logarithm n divided by n. So it can be reflected even in a one-dimensional setting, and also in higher dimensions we have absolutely the same situation. And maybe I would like to conclude my talk by some examples. First of all, let us take a uniform distribution on the unit disk centered at the origin. Everything can be calculated. So what is in this case Tukey depth regions? These are just disks of radius r alpha is the solution of this equation, and actually our theory can be applied, and we get such a limit superior and lim inf is equal to 0, so there are no surprises here. The second is Gaussian distribution. Just again, everything is satisfied. We can we can find this R. Actually, this is quantile, and actually Tukey depth regions are disks with radius alpha, which are quantile as here. And just again, we have a precise statement of law of iterated logarithm for these disks. But now let us take uniform distribution on the unit square. Here we have some problems, because depth function is not differentiable on this diagonal. On diagonals everything is good. It is not differentiable here on this line and also on this line. But so it does hold, because it is not differentiable, and moreover, we can see that our Tukey regions are non-smooth. But surprisingly, this is not a problem for us, because actually Hausdorff distance, an infimum which takes part in the definition of Hausdorff distance, is attained here only on diagonals, and in the neighborhood of diagonals the depth function is smooth. So actually this saves the situation, and even taking into account that d is not differentiable, we can apply our results, and actually we get lim sup of such a form in the law of iterated logarithm. And the last example is Cauchy distribution. As we have seen above, for Cauchy distribution, everything is unfortunately bad, because depth function is not differentiable. And if I will draw now the squares, which are Tukey depth, these squares, then the maximum distance between these two squares is attained just here on the diagonal. But on the diagonal, this function is not differentiable. So it is not possible to apply our results here because of non-smoothness of this function d. But actually, if we make use of all parts of the proof that can be saved, we can state the result in such a form. So lim_inf is of course equal to 0, but what about lim_sup in the law of iterated logarithm? We have only such inequalities, that this lim_sup between these two values, the second one is just square root of 2 multiplied by the first value, and it is clear why square root of 2, because square root of 2 is actually this distance. And exact value is, by our methods, is not known. And maybe I am over today. So thank you for your attention. Yeah.
Okay, thank you very much for interesting talk. And maybe somebody have questions or comments, please. I have several questions.
Yeah.
First of all, to the initial formulation of the problem. You said that the idea to measure the volume difference between the empirical convex hull and initial convex body looks not very natural geometrically, yes?
Yeah.
But what about the all Minkowski functional? We remember that convex body have a number of Minkowski functional, which characterize it quite good. So like not only volume, but surface measure, but like finite dimensional for dimension which is less than surfaces measure, and so on. Can you say something, or can you consider such Minkowski functional for this empirical convex hull, and to discuss its behavior?
Yeah, as a conjecture, as a setting, it looks very reasonable, but I'm afraid that for the whole class of all Minkowski functionals, it is hardly possible to get all these results, because it involves very careful study. Actually, we can have maybe some law of iterated logarithm functional over all these functionals. I think that is hardly possible. It is good proposition, but I am not sure that it can be done explicitly. Because
you consider the main technique is the set of half spaces, and one approach in the definition of Minkowski functional is like we have intersection with hyperspaces of different dimensions. So maybe it is good to characterize the measure, initial measure mu, not only by the this half spaces, but maybe some projections of this measure assumption.
I think it is possible up to some moment. So I think I will be able to formulate law of iterated logarithm in some maybe implicit form for the whole class of these functionals. But to translate this law of iterated logarithm in some explicit statement as we have, it is not so simple, because we used constantly that our sets are half spaces. Half spaces have quite good geometry.
Yeah. Okay. This is the first question, and second, we already began to discuss, because for empirical measures we have some of theorem about large deviations, and also we can study small deviations. So it is good to look at in this setting too.
Yeah, actually, large deviations was studied in a paper by Brunel if I'm not wrong now, it's about 10 years ago in probability theory and related fields. And there are many interesting results about large deviations. What about small deviations? I haven't seen anything in this direction, and it will be of interest. Yeah, I agree.
Okay, then as far as I understood, this is a beginning of the interesting project. So please keep us informed, and we are waiting for you with the next talk.
Okay, thank you. Thank you for the invitation.
Thank you very much. And Georgi, as far as I remember, maybe
Yes.
Andrei Pilipenko will
Yes,
be
with a probabilistic description of Brownian motions.
on the same star graph. Yeah.
Star-like graphs, yes.
Okay, good. Okay, then for today, that's all. Thanks, everybody, and see you next week. Bye.
Thank you.
Bye. Thank you, bye.